till long day after, today I will see, just as a review, what is the principal ideal. Principal ideal domain, properties of principal ideal, some question about this principal ideal, just as a review. This is today's goal of this lecture. At first, I will see what is the ideal. At first, I will see what is the definition of ideal. If this is R, ring R, with respect to addition and multiplication, R be a ring with respect to addition and multiplication, then the subset I is ideal. At first, I satisfy the properties of subring. If AB belongs to I, then that implies their subtraction always belongs to I, because it is satisfy the properties of ideal at first. If we multiply any element from right side, R dot A, this is belongs to this ideal. For all R belongs to ring and for all A belongs to ideal. Also, if we multiply from left side, then also this is belongs to this ideal. For all R belongs to R and for all A belongs to A. This is the definition of ideal. Oh, and the ring are always to ideal of any ring. That means for any ring, the set containing 0 and the ring itself always be an ideal. Second, every subring of Z is an ideal. Third, every subring of Zn is an ideal of Zn, and number of ideal of Zn is actually the tau n. Every ideal is subring, but converse may not be true. As for example, Z is a subring of Q, but Z is not ideal of Q. Why Z is not ideal of Q? If Mn belongs to integer, then their difference m minus n always belongs to integer. But if you choose one element half from Q, then half dot 4, half dot 3 equal to 3 over 2, which does not belongs to integer. So Z is not ideal of Q. That means every ideal is subring, but converse may not be true always. And number of ideal of Zn is actually the number of subgroup or subring of Zn is actually the tau n. If I be an ideal and 1 belongs to the ring, then obviously ideal equal to whole ring, because if R is the ring and 1 belongs to ideal, then R dot I belongs to I, and this is true for all R belongs to R. Therefore, R contain in whole ideal I, actually I equal to R. When the ideal contain the unity, then ideal I equal to actually the whole. Next I will say ideal generated by an element in CRE. Let A belongs to an element in the ring. Then ideal generated by A is written as AR such that R belongs to the ring R. Then this ideal generated by an element, this is in CRU. Always CRU is must. This is the ideal. Why in CRU is must? Because to prove ideal, consider two distinct elements AR1 and AR2 from ideal generated by A. Then AR2, AR1 minus AR2 which is equal to A times R1 minus R2. This is belongs to the cyclic subgroup generated by, and R times AR1. This is, we can write by associative property, AR1 times R, and R times AR1. Since this is CRU, so by commutative property we can write this as AR1 times R, and by associative property then we can write this as A times R1 times R, and this is belongs to the ring, means this is belongs to the cyclic subgroup generated by A. So this is with the ideal. So ideal by generated by an element, this is always true when the ring is commutative ring. Okay, OL. When F is field, then always there exist only two ideal, one zero ideal and another field itself. Why this is? Because when F is equal to field, then if one can possible, this is zero ideal, other consider A belongs to ideal where A not equal to 0. That imply obviously A is unit. If A is unit, that means since field, so every element has unit. That means since A is unit, that means actually A equal to whole field itself. So when F equal to, this is equal to actually whole ring R. When F equal to field, then there exists two ideal, one 0 and another is field. Now I will see our original goal of this lecture. What is the principal ideal? What is the principal ideal? In my previous video I had seen this part actually elaborately. Today I will discuss just as a review. Principal ideal is those ideal which is generated by a single element. As for example, I equal to 2z is principal ideal of z. Not only 2z, any ideal, mz type ideal is actually principal ideal of integer. I equal to ideal generated by 2x is not principal ideal of zx. Why? In my previous video this is actually I have seen, because ideal generated by 2 comma x means actually 2 p1x plus x p2x, where these p1x p2x belongs to zx. So ideal generated by 2 comma x, actually this is not generated by single element. So this is not a principal ideal of zx. Because ideal generated by 2 comma x means actually 2 p1x plus x p2x, where these p1x p2x belongs to zx. So ideal generated by 2 comma x, actually this is not generated by single element. So this is not a principal ideal of zx. What is the principal ideal domain? An integral domain R is said to be P.I.D. if every ideal of R is principal ideal. Number of principal ideal of field is 2, because we all of us know the number of ideal of field is 0, 2, 1, 0 and another the field itself. That means those integral ideal is P.I.D. whose every ideal is principal ideal. So the all field are principal ideal domain because the number of principal ideal in field is only 2, 0 and field itself. Every ideal are principal ideal, so they are, as for example, Z, Zi, R, Q, C, those are all P.I.D. because these are R, Q, C, these are example of field, and we all of us know in Z every ideal are principal ideal because in Z the principal ideal are look like MZ types. Zi also, in Zi every ideal also principal ideal because few days later we will show what is the Euclidean domain, and Euclidean domain always imply P.I.D. Zi is Euclidean domain, so Zi is implied, Zi is P.I.D. But Zx is not P.I.D. Why? Because in Zx ideal generated by 2, x contain in Zx. So this is not be P.I.D. So 1, 2 is P.I.D. Similarly 49 is 7 square. This is also P.I.D. 4 is 2 square, which is not prime number. So 2 is not P.I.D. 15 is 3 into 5. This is not look like p to the power n. So this is not P.I.D. I hope my all viewers have understood. Integral domain plus finite order is field. Since finite order integral domain is field, order of every field is p to the power n type. So if f is finite P.I.D., then f is isomorphic to Galois field of p to the power n. So up to isomorphism there is unique P.I.D. of finite order. Okay, I hope my all viewers have understood. Then which of the following is an R P.I.D.? Option 1 Z7I, option 2 Z7IX, option 3 Z5I, option 4 Z5IX. 7 is a option 1. Notice 7 is a prime number and 7 is congruent to 3 in modulo 4. Similarly 5 is a prime number but 5 is not congruent to 3 in modulo 4. So Z7I is a, since 7 is congruent to 3 in modulo 4, that means this is field. So Z7I is a P.I.D. And if this is field, then any polynomial ring, this is also field. But this is not congruent to 3, so this is not, 5 is not field. Sorry. This is not field. Since this Z5I is not field, so any polynomial ring does not be field. Okay? Over. I hope my all viewers have understood principal ideal domain clearly. This is actually just review part. Actually till long day, today I have defined ring theory just as a review. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.